There we go. All right, here we go, guys.
Okay.
Well, welcome to Monday Night Calculus. My name is Curtis Brown, and we are reviewing for the AP Calculus Exam 2024. I've got Steve Kokoska and Tom Dick with me. I'm really excited to just hear the tips and tricks and things that they've got up their sleeve, thinking about things that you need to be aware of and be practiced up on in order to be the most successful that you can possibly be on the AP Calculus exams coming up here in about 2 weeks, huh? Something like that.
Yep.
So, real excited to have you guys here tonight. And this problem set looks really engaging. I apologize, Steve. I'll just get
Oh,
out in
no.
front of it right now because I know the regulars are out there looking to see if I've done my homework or not. Tonight, I have not done my homework, which is relatively predictable. I've been on vacation. I'm still on vacation mode. So that's just the way it is. I'll let you guys get started. How's
All
that?
right, Curtis, if you would be kind enough to let me share my screen.
Oh, I suppose since you asked so kindly,
Okay.
I'll let you do it. You should be able to now.
All righty, let's see. That looks terrific. Well, thank you, Curtis. It's nice to have you back. I hope you had a nice time away from us and away from work. Well, we've got some good questions tonight, I think. Some typical free response questions that are calculator active and questions that involve topics or concepts, context that we think you might see on the exam that's coming up very soon. There are more than 9 points packed into these questions. We thought we'd give you a lot of different questions associated with each particular STEM here. I'm going to look at just the question, just problem one here to begin with. I'm going to hand it over to Tom. He's going to solve a lot of this using TI-84 technology. And then we'll come back to me for problem one, and I'll do a little bit with the TI-Nspire and talk a little bit about what students might have to present when they write the exam in order to receive full credit. So here we go with number one. We have these two functions, f and g, and they look pretty crazy. And let me just say one thing about this function f. I put this pesky plus 1.5 on the end here. And this is one thing that we talked about in the development committee when I was on the committee. I don't know, Tom, if you talked about this or not. But one change that they've made here is whenever there is a constant tacked on like that, a plus or a minus, to the end of sort of a complicated function, especially in a sentence in line as opposed to displayed in the center, we usually put that in the front, or not we, but the College Board will usually put that in the front. And the reason is we're not trying to trick any students. We just don't want them to forget that constant under the pressure of this exam. So there's a couple of crazy functions. F has got a sine of x squared over 2 and a log in it. G has got a product of an exponential and an inverse tangent. When I look at those, I think, oh my goodness, there's very little hope of me trying to integrate those. I think I could take a derivative, but I have little hope of actually finding a symbolic antiderivative of both of those. So one of the very first things I'm going to do, what I would do when I read this problem, before I even read any of the questions, is I'm going to carefully enter both of these functions into my calculator, and I'll show you how I did that in a minute or two. Here are some graphs of these functions. Y equal g of x starts out up here. Y equal f of x is this one. I think it's in blue on your screen. Here it is over here. And we have these two functions, pardon me, these two regions, R and S, which are bounded by these graphs, y equal f of x and y equal g of x. And so one of the things we want to do is to find the area of this region R. We want to find the area of that region S. We want to find a line x equal k, maybe it's about here, that divides that region S into two subregions of equal area. This is one of Curtis's favorite types of problems. I've added in here write but don't evaluate that expression, but you know what? We have such fancy technology that we might actually be able to find that value of k. While we've got this, I think we can do a couple of volume problems. We're going to take that region R and revolve it around the line y equal -1. I've drawn another graph later on, but y equal -1 is down here. So we're going to take this region R and revolve it about that line y equal -1. Then we're going to look into that region S in the plane, and that's going to be the base of a solid whose cross sections perpendicular to the x-axis are squares. We're going to try to find the volume of that solid. And then finally, especially for the BC students, let's see if we can find the perimeter of that region R. So that region R, again, is bounded by those graphs F and G in there, and I want to see if I can find that exact perimeter. So, wow, there's a lot to do in there. There's obviously a lot more than 9 points. And I'm going to turn it over to Tom, who's going to do an awful lot with the TI-Nspire, and I'll come back with the Nspire shortly. Tom, okay?
Sounds good, Steve.
All right. There you are, sir.
Okay. All right. So I'm pulling up a TI-84 emulator. And this is a really nice problem, Steve. Thanks for putting us together. It's, as you said, it's got more parts to it than you would see on a single 9-point question. But it's kind of a classic example of a type of problem that would show up on the calculator open part of the exam. It's got lots of features. And so it's a really great one for us to kind of illustrate what I'd call best practices when you're using your calculator on this part of the exam. So one of those things that Steve's mentioned already was getting these functions stored onto your calculator from the get-go. So let's go ahead and do that. Now, I think Steve took a special challenge to try to use every key on the calculator functions, at least as far as the function keys go. But let's just kind of dive in and get them entered here. So the first one was the sine of x squared divided by 2. And then it was plus a natural log of the quantity. Oops, I got an extra parenthesis in there I didn't really need. Natural log of x plus 1.
Right.
And finally, and Steve was pointing this out, don't forget that there was a constant added on plus a 1.5. So there's our first function. That was the function called f in the problem. And now let's turn to g. We'll put this one in y2. And this one was 3 times, oh, here we got an exponential going for us, e to a trig function. Oh, man, cosine x up there in the power. And then we'll get out of the exponent and multiply that by the arctangent of x. And I think that's got it. Good.
Good. Very good.
Okay. And just to get a quick graph, I might adjust the window a little bit here to make it look a bit more like what Steve had right on the exam. But this, I think a zoom decimal window is going to work nice to at least get a, see if we've got the, if we've entered things correctly. Now, the thing is, a problem like this, you would very likely have the graphs shown to you right there on the exam. They'd be part of the problem. They'd show you what these functions look like. And here we've got those. They're in the first quadrant here. So we can, oh, this is kind of interesting, this blue function, that would have been, I'll tell you what, let's just turn on the trace. Okay, the blue one was f. And I'm just looking to the left, it suddenly just seemed to be chopped off there. I wonder what's going on there. Let you think about that a little bit. Let's see. Looks like at -1, there's just graph disappears. And I invite you to think about the natural log of the quantity x plus 1. What's going to happen when if x is less than -1? Or even equal to -1, it's not going to be defined. And so that's why that graph looks like that. So we really got a pretty good view of the two regions, but I'm going to make it a bit larger I'm just going to go to my window here and just window. So we have more of the first quadrant picking up the screen. So let me move this over to, let's see. Give myself a little bit of space here, and then let's go ahead and graph this again. All right, so we see that region R is got the
That's
red
correct.
graph on top and blue graph on bottom, and then region S, those two graphs have switched positions vertically. And so those are our two regions. And the very first question Steve posed was parts A and B were to find the areas of these two regions. So we're going to need those. Actually, we're going to need 3 different intersection points where those two curves cross. So let's go ahead and calculate those. And this is a place where we can kind of illustrate some best practices.
Yep.
So let's go to the calculator menu, calculate, and we're going to calculate intersections. So I'll go down to number 5 there. And I'm going to go ahead and move over near that first intersection point. So the first thing I'm doing is just identifying the two curves. So let me hit enter. First curve is that blue one. Second curve is the red one. And then the third thing is to get pretty close to the intersection point. That's your initial guess. And then does an iterative procedure, not unlike Newton's method, to home in on that point. We're taking this as this is one of the allowed functionalities. It's using the calculator to solve an equation. In this case, we're solving where the two function values are equal. That's that intersection point. So that x value down there is one that I want to store away right away. I don't want to have to be like writing down 0.2198655 over and over again, or punching that in over and over again. So what I'm going to do is do a quit. Brings me back to the calculator screen. If I just go ahead and hit the X button, you can see that's the X, that intersection value is currently in X. Now we're going to find another intersection value. So what I want to do is safely store this away. So let's do a store. So it's going to take the last answer that I have here, and let's store that in A. And now I would do this on my test paper. I would literally write A equals this number. And then from then on, throughout my solution, anytime I wanted to use that number, I would refer to it as A. And the readers will be fine with that.
Yep.
If you declare, hey, look, I'm saying A is this number, whenever you use A, they'll take you for your word for it. And that's the way they'll read it. And so that's going to save you a lot of time and lots of chances to avoid errors and copy errors. Okay. Now we're going to quickly repeat that for the other two intersection points. So let me go back to the graph. Do the calculate again. Hit 5 for intersect. First curve. Yeah, I'm just going to say, yeah, sure. Blue one. Second curve's the red one. But now I'm going to move over to the second intersection point. Just need to get in the vicinity of it. Hit enter. And it homes in on it. There's the next intersection X value. We'll quit. Calculator screen. Pull up X. Notice it's a new value. Recalculated. And now I'm going to store that in B. And again,
Tom, could you, if you wanted to, simply do X store in B?
excuse me. Yes, Steve, that would work, I think.
You
I mean,
couldn't
I
you couldn't
understand.
hear my my head nodding and all the spider webs rattling around, but yes, that
Yeah.
That's acceptable. Okay.
yes.
Yeah.
And one other thing, Tom, too, I want to mention what you said about writing this value of A on the paper is certainly true, and we would encourage students to do that and then use A. But I think that when they write that value for A, they should write at least a minimum of 3 decimal places.
Yeah.
I mean, you don't want to just say, for example, that A is 0.2.
Right.
Exactly. Yeah.
Okay.
And I would even encourage the readers are going to want to see at least 3 decimal places of accuracy, either
Right.
truncated or rounded. But because we're going to be using these numbers for other purposes, for example, as the limits of integration on an
Right.
integral, I'd encourage people to go ahead and write it down to the value it had. And certainly you want to store it to as much accuracy as it has. So
Right.
for example, in this first value, I wouldn't look at that and say, oh, you know what, that's to 3 decimal places, that's actually 0.22
Yes.
because it's been around. And so I'm just going to use 0.22 as a bound for integration.
Hmm.
Well, cross your fingers, you might be lucky that that's accurate enough, but it's not, you've rounded enough that it could be that your subsequent integral calculation might be off a little bit. So you want the
Correct.
limits of integration, because this problem never actually asked for these numbers. We just need them to answer the questions
Hmm.
that were posed. Yeah.
Yep.
All
Thanks,
great.
Tom.
Thanks. All right, we're going to just do it one more quick time here. So
Okay.
let's do another calculate, and we'll do the intersection. Just enter the two curves again, and then move over near that third intersection point. Hit enter, iterates there. It's got the value x equal 4.3945. And now when I quit, I'll go ahead and take you guys' suggestion here. I'll just pull up X, and rather than take a look at it, let's just go ahead and store it. And let me be real creative and call this one C. Okay. All right. And so again, I would write down on my paper at least C equals 4.3945. But in my calculator, I'd have it stored this way. Okay. And then I could refer them to A, B, and C whenever I mean one of these three numbers. So now we're in a position to do some calculations that will give us results that will answer some of the questions we have. The first one, let me go back to the graph quickly. That's going to look at the area of this first region R, I think it was called.
Right.
And the red graph, if I lose track, I can always do a trace. Okay, the blue one is my function F. The red one is my function G. So I can see the red one's on top. So we want G of X minus, or Y2 minus Y1. Now on my paper, I'd be writing the integral from A to B, because this was my A value and my B value, of G of X minus F of X. On my calculator, I'm going to use Y2 and Y1. So let's go back to the calculation screen. Hit our math menu up. There's FN int down there at the bottom, number 9. Great, and notice I can now just put in alpha A for a lower limit, alpha B for an upper limit. And I think we'll have Y2 minus Y1. Let's see, I think we'll just bring up Y2.
But Tom,
Yes,
while
sir.
you're typing that, is there a reason? I mean, I know I know the way the calculator works to do that. Y2 minus Y1 dx will work just fine. Is it just for shortness of the statement that you don't put in the of x, use the function notation?
That's a pretty good point, Curtis. I actually tend to go ahead and put it in. And so let me go ahead and do that. Certainly on my paper, I'm going to be wanting to write G of X minus
right.
F of X.
Right.
Dx.
You don't want to do
actual
G minus
calculation.
F.
For the actual calculation, it doesn't matter. It's referring to y2 and y1 as the functions.
Right, and they're evaluated. I mean, they're functions, and they'll take the value at
Right.
that position X and do the numerical. But it just seems like, you know, just from understanding and just from notation showing that
Yeah.
even in the calculator itself, and that's just a heads up. It's a
Right.
little more clear.
Yes. Yeah. And I would write down A equals that decimal number, B equals that decimal number right on my test paper. I wouldn't then say, okay, y2 is equal to g of x, y1 equals. I would not put that on the test paper. I would
I agree.
use the function labels that were given to me for that purpose.
Right. Yeah.
That's the safer way to go. And this is actually, I think, a more acceptable, you know, in terms of the crunch on getting the calculation in. I went ahead with the y2 minus y1 and it'll be fine. But on my test paper, I would want to communicate that interval in a good format. So
Sure. Yeah.
good point. Good point. So that gives me my area, my region R, which could be reported either as 1.315 or 1.316. That's truncated or rounded. The readers won't care at all if you wrote down 1.315741. You know, if you wrote out more, they're going to read for the accuracy of those first three decimal places after the decimal point. So we got another region defined. Looking back at my graph, okay, that we're going to swap places here, and we'll be integrating from what we call B into C. So just kind of remind myself I need to swap the integram order here. So let's go back, bring up the integral again. This time I'm integrating from B to C. And this time we'll do a y1 of x minus a y2 of x. Now, if I had gotten confused somehow and gotten this order incorrect, for example, let's say I just copied my integral down and changed the A to B to B to C. What would happen is I'd get a negative number. Okay, this should be a positive number. If this came out as negative 3.29098, I would have known I'd had those swapped around. So that's something I could do as a reality check. And that's something you want to make sure you correct very, very clearly on your paper. Sometimes students will just like slap absolute value signs on stuff and say, okay, here's my actual answer. But you want to be really careful to communicate that clearly. I don't know if you may want to amplify that some more, Steve. But
yes, I will. Yeah, thanks, Tom.
But here I can see I've got the right order now, and this could be reported as either 3.290 or 3.291. So either one of those would be acceptable. And if you reported more digits than that, that's fine, as long as they're correct to that third decimal value. All right, okay. The one involving the vertical line, Steve, dividing the region into two areas. Now that's just going to be what was asked for in that part was just to put down the equation that you can use to solve for that. So I think I'm going to defer on that one, let you talk about it.
Okay.
I will switch over to this next one. And this was I'm going to go, has to do with revolving the region R around a horizontal line.
Correct.
I'm actually going to go to my y equals and put in that horizontal line. I think it was y equals -1. I'm going to put that in as my y3 graph again. And there's that black line. So we're going to take this region R we're going to revolve it around this horizontal line. That's going to generate a solid revolution. We'd like to find the volume of that. Okay, so what's that going to look like? Well, let's go back. Well, first of all, before I go to that, let's see. It looks like the cross sections of this, well, if I take a single cross section, I'm going to have a vertical segment that's rotated around a line. I think that's going to give me something that looks like a washer. Okay. And so, I encourage people to think through that as what would a single cross section look like when you're revolving around? That'll be your guide to setting up that integrator. So let's go back to our calculator. Whoops, I hit the mode there. Let's see. Didn't mean to do that. Okay. And let's see. So I'm going to have pi. I'm going to go ahead and get our pi in front of the integral. And now I'm going to integrate from A to B again. And here's where, whoops, let's see. Sorry about that. Put the wrong key. There we go. Alpha A. Go up to alpha B. This is where, having written those down once and for all, and be able to refer to them this way is going to really pay off huge dividends.
Agreed.
Okay. And the pi times a radius squared. So I've got to think about what is the radius. I'm going to actually go back to the graph. Think about that. It's going to be the outer radius would be this red graph, that function value plus one more unit, because we have got one additional unit to get down to y equals -1. So when I go back here, my integrand is going to be y2 of x.
That's a pretty
+1.
handy, I like that handy shortcut to get the Y2, Tom.
Oh yes, that's one Curtis has finally taught me how to do it. Well, I mean, he's tried for many years.
I've tried for a while, Tom. That's you've
I
just
tend to
finally
just go to the
listened.
bars menu and get it that way, which is only so y2 of x plus 1, that quantity squared.
Mhm.
All right. And then we're going to subtract the inner radius of that washer, that area, and that's going to be my y1 of x plus 1. That's because of that extra unit you had to go down to get down to that line, y equal -1. That quantity squared. And you notice I had the pi, some people might write pi times each of those individually. I just factored the pi all the way out to the outside. And now we'll let it calculate. And it's amazing how fast that is. That's it. Hopefully that's the same thing you got, Steve, when you did it. So
Okay.
all right. And let's do, I'll tell you what, Steve, maybe I'll do one more and then turn it back over to you. I'll let you do both the dividing line and the perimeter. Okay.
Deal. Okay.
So
Yeah.
So this last one was a region S this time, where let's look at that graph again. S is this part here, kind of between about a 1.5 to 4.5. Where each cross section is the base of a square. So each cross section that's perpendicular to the x-axis. Okay, well those cross sections are just going to be y1 of x minus y2 of x will give me the length of that segment. If that's the base of a square, then the cross section would have an area of that quantity squared with no pi involved at all. Okay, So let's go back to our calculator screen. Let's see, I believe, let's see. Well, let's just go ahead and do it from scratch here. We're going to be integrating from B to C.
Correct.
And let's see, we're going to take the quantity y1 of x. I forgot a parentheses there, so let me get that inserted. There we go. Y1 of x minus y2 of x close off that parentheses. So it's that quantity y1 of x minus y2 of x, that entire quantity, I want to square that. That's going to give me the area of that square cross section. And some people, when they see these integrams with the squaring of some quantity, they want to knee-jerk throw a pi in there. I see it so many times. Okay, that's going to work for those solids of revolution, but this thing is not that. We've got exactly the cross-sectional area function here. And move, let's go, and there we go. So again, this would be
Pretty good.
4.509, either truncated or round. That'll be the value. Okay. Well, I've kind of monopolized a lot of this, but this was such a wonderful problem, Steve. Thanks for putting it together. Because it shows off, getting those functions stored in your Y1. Also, doing the reality check. Yeah, my graphs look just like the one that's presented on the test paper, and then taking advantage of storing these values away, labeling them clearly, and then you can reuse those labels in your discussion of your solution. The readers are going to be, I will guarantee, more than happy that you're doing it that way, because you really are showing a good use of mathematical notation and doing it in a very efficient way. All right, Steve, I'll unless there's something you'd like me to look at.
Sounds good, Tom.
I've left a couple of parts for you to address, and I'll just stop to share and turn it back over to you.
All righty, I'll see what I can do here. Let's see, where did it go? There it is. All right, how's that, Tom? Okay, Curtis, you can see that?
Looks good.
Yeah. All right. All right, so I'm going to take a look at this problem, a couple of the other parts that Tom did not look at, but also some of the ones that he did, and show you how I might do this, solve this on the Nspire, and also try to hit upon how or what students would have to present to receive full credit on the exam. So one subtle point I wanted to mention about this graph up here, Tom is absolutely right. In a problem like this, if this were given to students on a free response, it is most likely that they would also be provided with a graph. But one subtle thing I think I've noticed, and correct me if I'm wrong, Tom, is they don't always tell you which graph is G and which graph is F. So that might be something that would be incumbent upon the student to get these graphs, get these functions entered into their calculator and identify those. Just a subtle thing, extra thing that they would want the students to do. So when I see a problem like this, the very first thing I'm going to do is I'm going to work to enter those functions into my calculator. I know I'm going to have to use them quite a bit. So I did that on my TI-Nspire. There's my function F, and there's my function G. One advantage to using the Nspire is that I can use the actual variable names that are given to me. That just makes it just a fuzz easier, I think, to work with these functions. Now, Tom found these intersection points, the x coordinates of the intersection points, by actually doing this on the graph screen. And I can also do that on the graph screen here, but there's a very nice built-in command on the Nspire called zeros. And I think you've heard me talk about this before. I like to use this function zeros. It's going to find places where f of x minus g of x is equal to 0. And I've added in an extra condition over here. You can see that vertical bar such that x is between 0 and 5. Well, how did I know that? I knew that by looking at the original graphs, either that were given to me or that I produced on my calculator. Now, the advantage, in my opinion, in using the zeros command is that it automatically produces a list of all of the solutions. Yes, you're right. I know Curtis is going to remind me of this. There is a command built in here to the Nspire that will convert solutions, for example, to solve automatically to a list. That to me is sort of an extra step that I need to take. So that's why I like to use zeros. So looking ahead just a little bit, I took the first expression, first value out of that list, assigned it to A, the second value to B, and the third to C. I have my calculator set to display 3 digits of accuracy, 3 digits to the right of the decimal rounded, and so that's what you're seeing on the screen. I'll talk a little bit more about what we might have to write on the next page. Now, I can also do this on the graph screen. As you can see over here on the bottom left-hand side, I drew those graphs on the TI-Nspire. I found all the intersection points. I also have all the y-intersection, the y-coordinates. Now, there's some sneaky ways to assign those values to A, B, and C right here on the screen. I still prefer to do it on the calculator screen as I did in the top right. Now, before I write anything here, I'm going to show you this definite integral on the calculator screen. It's the definite integral A to B of the way that I think about this is y high minus y low, the high function minus the low function. I'm finding an area bounded by two curves between A and B. The upper curve is G, the high curve is G, the lower curve is F, and there's my value to 3 decimal places, 1.316. I hope that's the same thing Tom got.
Say, Steve.
Yes.
Apologies. I just want to make sure people realize that on the Nspire, as you mentioned, you set your calculator to display 3 digits accuracy, but internally, those numbers are still retain
Yes, sir.
much more precision. So there's no the caution I gave of kind of prematurely rounding and then using the rounded number. Steve has not committed that error at all. He's just displayed them that way, but those numbers still retain their accuracy. That's really nice and good. Yeah.
I would follow that up also. The zeros command that you used over there is a CAS only command, so that list generation can only really happen utilizing the CAS machines. Mm-hmm.
So on the non-CAS machine, can you use solve or nsolve?
Nsolve, yeah.
Yes.
Mm-hmm.
Okay.
Nsolve would work just fine, but you do it one at a time that way.
All right. So one more graph screen. Sorry about this, Tom Curtis. One more graph screen. You can also find this definite integral and display it, sort of visualize it on the graph screen. You can see that shaded area here. This is the region R. And I calculated the area of that region R on the graph screen, and I got the exact same value, which is good. I feel good about this answer. Now, what do you need to write on your paper here to get full credit? Well, I have written here A to B, G of X minus F of X is 1.316. It's not quite enough. Somewhere in here, I've got to identify what the values are for A and B. In recent past, we've actually seen the first part of a problem like this is something like find the X coordinates of the intersection points. Now, if that's not part of the problem, if that's not explicitly asked for, then of course we've got to identify A and B. And I did that on my calculator screen. So A was equal to, well, it was what, a 0.219, I believe. and B was equal to a 1.453. So I've got to have something like that on my paper. And Tom and I have talked about this a lot, Curtis. It's funny over the years how little you actually have to write to receive full credit here. So there's a lot going on conceptually that the student has to think about and write down properly, then go to their calculator and get an answer. So they've got to write the definite integral from A to B, g of x, f of x, minus f of x, go to their calculator and get that answer. This, coupled with this, would get full credit. Let me write a couple of other things here, some common errors that Tom and I might see, okay? So we might see something like this, the definite integral from A to B of f of x minus g of x. A student might write that, and they might go to their calculator and get the opposite or get a negative value and realize, oh, wait a minute, it's got to be positive. So I'll write the positive value in there. It's 1.316. Well, that doesn't get full credit. And the reason is because this definite integral is not equal to 1.316. It's the
Right.
opposite of that. It's the opposite of that. So how do you fix something like this? Well, a couple of ways. You could recognize that you have mislabeled the high curve and the low curve, go back and write it correctly like it is up here, or you could say something like, well, wait a minute, this is equal to negative 1.316. And then below that say, oh, well, the area of the region R is 1.316. What you don't want to do is you don't want to connect this and make what we call a linkage error and just say, oh, well, this is equal to 1.316. That's very bad. That's wrong. And that won't receive credit. Okay? Good. I think I've got everything in there. Did I forget anything about that grading, Tom? Anything else that could go wrong in there?
No, I
Oh,
think you covered it.
I got one more thing. Thank you, Tom.
Oh,
One more. What about the student who does something like this and leaves out the dx in there? Okay. Well, in general, we're not going to penalize the student who gets the right answer here. I mean, suppose the dx were left out.
Kind of like you did, Steve.
Kind of like I did there, yes. If the dx is left out and we still have everything else correct in there, it's pretty clear what the integrand is. And so that student would receive full credit, I believe. Depends upon who the chief reader is, that's true. We always encourage students to use correct notation. We're stressing notational fluency here, but I think that would receive full credit. Hey, let's move on here a little bit. So how do we find the region, pardon me, the area of that region S? That's the shaded in region over here. Well, okay, that's a definite integral from B to C. This time the high curve is F, the low curve is G. So that's f of x minus g of x dx. I think that's a 3.219. I think that's what you got, Tom. And I'll add in off to the side here. Again, we need to know what B is. It's 1.453. We need to know what C is. C was a 4.395, I believe. And by the way, if B were identified up in part A, you would not have to re-identify it in part B. So once it's identified in a problem, we're okay with that. One other little thing too I thought of. Look, the functions f and g are given to us explicitly, and as Tom pointed out here, these are pretty complicated. They take a little bit of time to enter into your calculator. And you know what? They take a little bit of time, even if you wanted to write them out by hand. So if a function is identified, is defined explicitly on the paper, on the exam, don't take the time to write it out in here. Because if you make a copy error, if you make a mistake in copying, even if it's a -1, even if it's a negative sign, even if it's a square missing, you will not get full credit because what you have written on the page will not be equivalent to what you have over here. You may use the correct functions in your calculator, but you have not written it properly on your paper, and so you will not get full credit. Let's take a look at C. All right, so the region, pardon me, the line x equal k divides this region S into two subregions of equal area. Well, there are a couple of different ways to do this. Here's how
Oh, I do have
yes,
a question that just came in. Could a student use, I know you said they can't just drop in the negative sign or drop the negative sign. Could they use the absolute value signs? I suppose they'd have to do it on either side of the expression to fix that negative answer.
yeah, they
Just as
could.
advisable to do what you did and say, hey, I got this negative. The area between F and G is positive or whatever.
Okay, so here's sort of a general response to that, Curtis. As long as what the student has written is mathematically correct, they will receive full credit.
Okay.
So if they were to put absolute value symbols around the entire integral on that one, is that an expression for the area? Yes, it is. So if
Okay.
they put absolute values around everything and set that equal to plus 1.316, yes, that's correct.
Okay.
Okay.
Okay. Good.
All right, so
Yeah.
let's see. I'm going to actually arrow down just a little bit here so that I can look at this x equal k. This is my line here that I'll call x equal k. It splits this region S up into two parts of equal area. And I'm going to write an expression that represents this area and write an expression that represents that area and equate them. So over here on the left-hand side, that's an integral from b to k of f minus g dx. And on this side, it's the integral from k to c of f of x minus g of x. And that's an expression that is an equality that if we could solve that, would give me that value of k. It turns out that you can actually do that with the TI-Nspire. I was actually able to solve that for k. It's about 3.27. There are some other ways, some other expressions, some other ways that we could write something like this. For example, Curtis, given what we have done in part B, can you give me another way that I could write an expression involving an integral?
In part B.
Well, given what we did in part B, where we found the area of that region in S,
Oh, sure. Uh-huh.
so we found that area to be, what was it, 3.291.
I
We could
suppose
actually,
you could integrate. Here's what comes to mind. I don't know if
okay,
it's what you're thinking, but
okay,
you could integrate from 0 to K and set it equal to half that area.
beautiful, from B to K, exactly. I could set
Or
either
sorry,
one.
yeah, whatever, B to K. And yeah, and then set it equal to half of 3 point whatever it was,
Yep,
291,
yep,
and
exactly,
give yourself that.
exactly.
Again, you're solving for K, right?
Yep,
So
very good. Excellent. Excellent, Curtis. Yeah. And I think there are some other expressions that we might be able to use too. There might be another one that we could come up with. Those are the two, I think, most common ones. All right, here's a picture. I want to take that region R and I want to revolve it about the line y equal minus 1. Tom talked a little bit about how we figure out what those radii are. Here's how I do this, okay? So I'm going to take a look at this region R up here. And the first thing that I recognize is that the axis of revolution is not a bounding curve. So that says to me that this is going to have to be computed using the Washer method. Following my train of thought, what I need to do is to find an outer radius and an inner radius. So what I do is I draw a line perpendicular to the radius from the outer curve, perpendicular to that axis of revolution, that's my outer radius, from the inner curve to my axis of revolution, and that's my inner radius. And now I can visualize a little bit more about how to express R sub O and R sub I. So that outer radius is g of x minus a minus 1, high minus low, squared. All right, the radius is g of x minus a minus 1. So I'm going to take pi times that squared. The inner radius, f of x minus a minus 1, f of x plus 1, and I'm going to have to subtract that off, squared. So there's the exact same expression that Tom wrote into his calculator. That's the one that I arrived at. What would a student have to write on their paper? Exactly this. Okay, with some values for A and B given. Go to their calculator, obtain an answer, come back and write in here 3 decimal places. I think that's 33.644. That's a nice problem. I really like that one a lot. You have to think a little bit about what the outer radius is, what the inner radius is. It's often very difficult to grade because students have very different ways of writing these radii. But that's a nice problem. I like that one. All right, part E. Holy Toledo, let's go back to this region S. And this time, the region S is the base of a solid. If we take a plane and we cut down into that solid S, the intersections, the cross sections perpendicular to the x-axis are squares. I've tried to draw one of these, if you can picture this coming up from the paper. Here's the square, and the side of one of those squares is the high curve minus the low curve, or f of x minus g of x in this case. And so the way that I try to figure these out is before I even get to an integral, is I think about, well, what is the area of that cross section at an arbitrary point value x as we work our way across the region S? And so the area is going to be a side squared, area of a square. And so that's f of x minus g of x squared. So the volume of this solid is simply B to C, okay, with B and C defined over here, of f of x minus g of x squared. There's a dx on the end there. And I think that's the same answer that Tom got, 4.509. Fantastic. I do want to remind everyone, again, Tom is absolutely correct. Sometimes when students under the pressure of an exam say, well, look, when I'm doing a volume problem, I have to have a pi in there. And sometimes they will incorrectly add a pi in here. Sometimes if they're dealing with a geometric region, even if it's a square or a triangle, they'll add a square root of 3/2 in there as a constant times this. Don't need that. We've got the area of an arbitrary cross section. Cool. Oh, and there's more. How do you find the perimeter here of this region R? Whoops. Let's go back over there. Whoops, I'm sorry. We're a little ahead there. Here we go. There we go. All right, so where's R again? It's over here. It's that first region. So I've got to find the length of that curve from A to B, the length of this curve G from A to B. So this is a BC type problem. This is going to be 2 separate definite integrals. Square root of 1 plus f prime quantity squared dx, 1 plus g prime of x squared, A to B. Yikes. I don't think I want to do that one symbolically. Remember how complicated those two functions, f and g, were. I think I could find the derivative analytically, but I don't want to. I did this on my calculator. I did this with the TI-Nspire. So you can actually write in here, this is an expression for the symbolic derivative of f, and I'm going to square it. Symbolic derivative of g, I'm going to square it. 1 plus that inside the square root. I've still got a and b stored, and I added those two values together for a 5.538. There's a nice problem. What would you have to write on your exam paper for this one? Well, you'd certainly have to have a line like this, indicating those two separate sort of perimeter pieces. And then I think you could go directly to the 5.538. Cool. Curtis, any questions now? Any other questions on number 1? Or can we at least take a quick look at number 2?
We have had no other questions, just talk of mutiny, but don't worry about that.
Mutiny, okay. All right. Well, let's see what we can do with number 2. Maybe I can look at a couple of parts and and Tom can finish up with the 84. All right, so a particle P is moving along the x-axis, and this time we're given its velocity. For time t greater than 0, there's a crazy velocity function which has an exponential, a log, and a trig function in it. The position of the particle at times t equals 0 is at -3. What's the first time in the interval between 0 and 5 where the particle changes direction from left to right? And give a reason for your answer. Well, as Tom, I think, would attest, one of the very first things we ought to do is to enter this function into the calculator and store it. So I did that on my TI-Nspire, and again, I can use that variable v, so I did that. I think that looks right. I've got the minus t squared over 10 all up there in the exponent. It looks kind of funny there. It looks kind of large, but I think that is all up there in the exponent.
Well,
and once again here, what I did is I'm going to kind of go back and forth with my calculator screen and my graph screen here to solve this problem. I think what I did after entering this v of t is I actually graphed v between 0 and 5. And I looked at this point over here where the function, where the curve v crosses that x-axis or t-axis in this case. That to me is going to be the quote unquote answer, the t-value that I'm looking for, because that's a place where v changes from negative to positive, where the velocity changes from negative to positive. That's the first place where the particle changes direction from left to right. Now, I found that value of t on the graph screen. It's 4.311. I also found this on the calculator screen using my favorite command again, zeros. There's the 4.311. What would a student have to write on their exam paper? Well, I think they'd have to give us some indication that they're looking at places where v of t is equal to 0. Those of you who have been preparing for the exam and looking at old questions will frequently see that one point is given for setting v of t equal to 0, and other problems for setting the derivative equal to 0. It's a conceptual idea. I know that I need to look at places where the velocity is 0. I did that. I found two candidates between 0 and 5, but I know the answer is 4.311 because, well, I've looked at a graph, or I've even considered some values of v to the left and to the right of both of these t values. So the first time in this interval where the particle changes direction from left to right is 4.311. What's the justification here? What does the student have to respond with? Well, at this time, the velocity changes from negative to positive. Good. Find the speed of the particle p at time t equals 4. That's a pretty easy one. All I really need to do is to find the absolute value of v of 4. What would you have to write on your paper here? Well, what's your mathematical expression? I'm finding the absolute value of v of 4. It's 0.166. There it is on my calculator. Very straightforward. Conceptually, I have to know what speed is equal to. I have to know that formula and write that down, go to my calculator and get an answer. In part C, I'm going to do this one, and then Tom, if you have any last thing that you want to end up with, and I like this one. Is the particle speeding up or slowing down at time t equals 4? I'm almost unwilling to bet the farm that we'll see a question like this on the exam in a couple of weeks, and explain your reasoning. What do you have to do here? Well, sort of the traditional way to do this is to evaluate the velocity at 4 and the acceleration at 4. We know that the acceleration is the derivative of the velocity. So I did that. I found the velocity at 4 is minus 0.166. The acceleration, the derivative velocity at 4 is 0.427. So because v of 4 and a of 4 have opposite signs, the particle is slowing down at time t equals 4. On your exam paper, if you were doing this, if the question does not ask for these values explicitly, you do not have to give the value of the velocity at 4. You do not have to give the value of the acceleration at 4. If you do give those values and you give them incorrectly, you will lose a point or you will not earn a point. If it asks for the value, of course you've got to give it. If it does not ask for the value, a test-taking tip is, well, you don't have to report it. All I have to really say is that V of 4 is less than 0, A of 4 is greater than 0, the particle is slowing down. There is one other sneaky way to get this answer, and that is, well, I can take a look actually at the derivative of the speed. The speed, remember, is the absolute value of the velocity, and the calculator can actually figure this out for us. This was sort of a revelation to me a couple of years ago when a student had actually done this on their paper. And I realized, oh boy, that really does work. That's not something that we would think about without technology. And so the derivative of the speed is negative, and that tells me that it's slowing down, decreasing at t equal 4. Tom, do you have a last minute TI-84 tip?
Just this, Steve, and that's I'll just share the screen really quickly here. On the 84, your function plotter is going to be functions of x. And this is a case where we had a function of t. We often encounter those.
Yes.
It's just a translation you'll need to make on your calculator. Is I would still use x as my independent variable. And so here I've entered that function with x instead of t, and this is the velocity function. Entered it into y1, and then I can interpret it. Now I'm really interpreting this horizontal axis as my t-axis, and my vertical axis is my velocity axis. And as you said, at v of 4, is it slowing down or speeding up? Well, velocity is negative. The slope of the velocity, the acceleration is positive, slowing down. Yeah, which means that its absolute value is getting closer to 0. Yeah, it's decreasing. So,
Cool.
Great job, Steve. So
very cool. So, Curtis, we do have some other questions and answers. I think our third problem is a very nice rate in, rate out sort of problem, which I'm guessing that the students will see this year also. And we'll be able to post those answers, questions and answers tomorrow morning, I think.
Awesome. Yeah. We'll make sure that those questions and answers are up there. In the YouTube description here, down right below this video, we'll have those questions and answers there, so that teachers can download those, use them, refer back to this session, and get ready for that AP exam. We will be returning in the fall to do a new round of Monday night calculus sessions. We'll be kicking that off sometime here this fall. We'll get the word back out into the Facebook community for that. But until then, this is us. We'll sign off here, and good luck on the AP exam.
Good luck.
Really study up, and I know you'll do fantastic. So we will see you in the fall.
Terrific.
All right, guys.